Now let's look at the same problem in the ensemble theory. Now, what do we do in these ensembles? We have many copies of the same system. N of them. Now, if you compare with the microcanonical ensemble, in the microcanonical ensemble, we said that energy is fixed, so all these copies are fixed, have the same energy. The total number of was fixed, and eventually we were led to the conclusion that the probability of every microstate should have been equal. Now we don't have fixed energy, so there are many copies in this ensemble having different energies, but I still want to fix one thing. The average energy, I would like to fix it. Of course, I have an R being the number of copies in the R microstate, in the microstate R. Now, of course, now in the microcanonical ensemble, all these microstates have the same energy, but here I have all microstates corresponding to all possible energies my system can have. The only thing I'm keeping fixed the volume, I'm keeping fixed the number of particles, but the energy is not fixed. What I want these NRs to satisfy is sum over all possible microstates. This should give me the total number of copies in my ensemble. And furthermore, if I have number of copies in the rth state multiplied by the energy in the rth microstate, divide by the total number of copies, well, this is nothing but the average energy, this has to be U. This is also fixed. These are the only things I'm fixing. I'm saying that my system has some average energy, and the total number of copies in my ensemble is given by this huge number. Now the question is, how many different ensembles I can create? And what will be the most probable distribution of these numbers NR? What the most probable, we will also look at the average distribution of these numbers NR. So that is the question. Well, in the microcanonical ensemble, the energy was fixed, so I only had the first constraint, not the second one. But now I'm letting the energy free, the average is fixed. So that second constraint is kind of what will cause many difficulties, let's say. You see, if I would like to count these, let's say that I have the first state, the ground state, first state, second state. I somehow label my states. The possible ensembles I can have, let's say, all of them might be in the. This is in the microcanonical ensemble. I'm not imposing this constraint yet. All of them might be in the first ground state. All of them except then one can be in the ground state. That one can be in the first state. Or, I don't know, there is no state in the ground state, 1 in the first excited state, n-2 in some other one, 1 in some other one, zeros in all the rest. Well, I mean, you can just, if you like, tabulate all possible ensembles. But since n is already a huge number, you will have a huge number of possible ensembles you have. But I repeat, the ensembles, I wrote over here, they don't satisfy my second constraint. Among all these possibilities of these NR numbers, I have to choose the ones. I said this is called an integer partitioning. Of n. Among all possible integer partitioning, I would like to find the ones that satisfy the second constraint. I should pick them one by one. Well, that is one option. An alternative one would be an alternative approach. Well, you see, here I will have a huge number of copies. Among those huge numbers, I should just pick up huge copies. I can just go ahead and try to find the ones that already satisfy both of them. For example, what I can do, I will have many microstates many copies. No, these are microstates, not copies in my ensemble. Microstate, I'm just putting the numbers. How many copies in my ensemble are in a given microstate? And then I can say, well, let's say one of these states, I'm looking at the macroscopic system, the energy levels will be almost continuous. So there will be a state which has a given energy equal to my average energy. So for example, if all the copies in my ensemble are within that state, both constraints are satisfied. Well, I can pick one of those copies and assume that it is in a higher energy state, let's say over here. But if that is the case, I still would like to conserve the average energy. I should put another one in a lower state. So there should be some 1 over here. I'm left with n minus 2 copies over there. And then I'm just trying to change the positions of these n numbers one by one. But what I need to do is I have to make sure that if I move a state to a higher state, then I should move another state to a lower energy state. Now, counting that will be highly complicated. I mean, I will make a huge simplification. And remember, we are dealing with huge numbers. When I'm counting the number of states, even if I don't count all of them, but if I count 1 in 10 to the power 20, well, that's fine. That's an acceptable error. I don't have to count all of them. The only thing I have to be sure that I'm counting the huge part. And well, let's say that I have another copy with let's say n minus 10 of them, 2 here, 1 here. All the others are distributed. I can create another possible ensemble by just dividing these two into 1 and 1 between 2 states that have almost the same energy. You see here, if I moved one of these copies to a higher energy state, I had to move another one to a lower energy state in order to be able to conserve energy, to satisfy the energy constraint. But if I just shuffle the particles among states having the same energy, I don't have to do that. So just shuffling particles between states having degenerate states, well, I mean, the second constraint is already satisfied. I'm creating a new ensemble. I'm changing the distribution of microstates. That's the new ensemble. But if the initial ensemble satisfies both constraints, the shuffled ensemble also satisfies both of those constraints. So that will be essentially the trick I will be using. Let's say that I have all these levels. Infinitely many energy levels, in fact. And they are very tightly packed. I will divide these tightly packed states into groups. Let's say here I will assume there's a group. Here I will have another group. Here I will have another group. Let's say that in each one of those groups there is GR of them in that group, GR prime, number of different microstates in that other group. Let's say that I will assume that there are NR copies in that group, NR prime copies in the second group.
G is the number, right?
G is the density of microstates. Because I have all these, I have my ensemble, which is just a huge number of copies of the identical system. I don't know which microstates they are in. The possible number of microstates are, in fact, will be infinite. But I'm just grouping these microstates into packs, cells, each of which have almost the same energy. And the number of states in one pack is GR, in another pack is GR prime. How many copies in my ensemble are in this pack with GR states? There are NR of them. And then I have NR prime of them in the GR prime cell, etc. So kind of my notation has been modified. Before I was using R to denote the microstate. Now I'm using the symbol R to denote these packs of microstates. And the only thing I'm assuming is that within a pack, the states are degenerate or almost degenerate. So let's say that I have one ensemble that satisfies both of my constraints. Then just shuffling these NR states over these NR copies among these GR states will give me a new ensemble satisfying the same constraints. No? Let's just imagine him sitting on the third row. Okay? Let's say that my constraint is, on the average, I should have two people on a row, on those two rows. Well, let's say that, no, let me change it. Let's imagine each one of these rows is one energy state, microstate. And let's say that my constraint is that, I have an energy, average energy, the number is fixed, the total number of copies is fixed. Then I can say that the average number of particles in each row should be 1. But I cannot distinguish the first row from the second row. So how many possible in how many possible ways I can distribute you? Well, I put two people in the first two rows, two people in the last rows. If I shuffle these two people among the first two rows, on the average I will have one student per row. If I could distinguish these two, I could have said there's exactly one here, one there. But since I'm vague, I cannot distinguish it. The only thing I will impose is I have just two of them here, two of them over there. Shuffling the two among these rows, well, nothing will change. I will still satisfy my constraint. Similarly over here, what I'm saying is I will have, let's say that I have one state here, one copy here, another copy over here. This is one ensemble. Or I can have one copy here, the other copy is also there. Well, the distribution is now different. I have a new ensemble, the distribution among the microstates. But since these two, this configuration and this configuration, they have the same energy. I cannot distinguish the energy levels. Since they have the same energy, just moving this copy from this microstate to that microstate, I'm creating a new ensemble, but I'm not violating any of these constraints. This is already satisfied. I'm just moving one from one microstate to the other one. This is also satisfied because as I'm making this movement, moving one copy from one microstate to the other one, I'm not changing its energy. So Although NRs will change, the energy of that new R will be the same. So I'm already also satisfying the same second constraint. Now, if I shuffle these NRs, not among themselves, but within each one of these cells, all of the new ensembles, they will satisfy both of my constraints. Of course, I'm missing some possible ensembles. Which ones I'm missing? For example, I could have taken this one, moved this copy and moved it here. At the same time, I could have taken this one and moved that copy to some state over there. Now I create a new ensemble which would satisfy both of the constraints. But I'm not counting them. I'm only counting the shuffling within each cell. This will introduce an error, definitely a large one. It will probably be, I will be off in the number of possible ensembles by a factor of, let's say, n. But so what? Since we are dealing with huge numbers, I will be eventually taking the logarithms. The logarithm that I'm interested in scales as n. The error I introduce will scale as logarithm of n. It is negligible. But then now, from one copy of my ensemble, I can just create other ones by just shuffling within each cell. So the question is, how many possible ensembles I can create from such a distribution of the number of copies in a given cell? This will be equal to for the earth cell, let's say, each one of the states can be in any one of those NR state, each one of those NR copies can be in any one of those GR microstates. So the number of ways I can distribute those NR copies among those GR states will be just GR to the n factorial. GR to the power n, sorry. But I should also divide by NR factorial, because just changing their order shouldn't change anything. Do I have? Yeah, I think I should have that n factorial. No. Easy. Just take each cell. Okay. Each cell corresponds to, let's say, a given microstate. You can just assume that they are degenerate. There are GR degenerate states with GR states degenerate with the microstate R. And there are NR copies in my ensemble. Each one of those NR copies can be in one of these GR degenerate states. So the first one, how many possible ways I can distribute these NR copies in my GR states? Well, each one can go to GR of these microstates. So in total, I have GR to the power NR possibilities of distributing my NR copies among these GR states. This is for the GR state. There's a similar factor for the GR R prime state. And basically, I need to multiply over all these cells. So for a given distribution of my copies in these cells, there are this many different ensembles I can create.
R is the number to extract. numbers?
No, R is the label of these cells. Yeah, I'm summing that product over R basically means that I'm multiplying over each one of these cells.
And what did they say for the left-hand side?
Left?
Left-hand side. What did they say for that?
Well, that is the, you see, if you give me an R, those are just the number of copies in each one of those cells. Okay. Now I ask you the question: how many ensembles can I create that have those numbers NR? Well, I'm taking many different copies here. My ensemble is itself an infinitely, very huge number of copies of my identical system. Then I'm asking you the question, what are the possible ensembles I can have? In the sense that, well, in how many different ways this ensemble can be in the microstates available. And then you come up with, oh, I know the number, let me just, you say, then I say, let NR be the number of states, number of copies in the cell. What is that cell? Well, that cell is a correction of GR microstates. You still don't specify me what that microstate is, or which copy is in which microstate, but you just tell me that there's a group of microstates over here, and NR of my states, of my copies in the ensemble, are within those, are distributed among those GR states. So different distributions of those copies among these GR states will give me a different ensemble. So there are this many ensembles that correspond to this given numbers NR. Now I ask the question, what is the most probable value of NR? Now let me take the, rather than maximizing omega, as usual, let's take the logarithm. Because when I take the logarithm, the product becomes sum. Now I will be trying to maximize this subject to the constraints to these two constraints. So I can basically look at the variation of logarithm of omega plus, let's say, alpha and r minus n plus beta this should be 0 as I change these numbers and r's. Well, let's just look. I also know what logarithm of omega is, so let me just write this term. It will be sum over r variation of nr times logarithm of gr I think I'm missing something. I think I need to divide this by n factor. Because if I just change these NR's copies among themselves, I'm not really getting a new ensemble. The distribution of microstates doesn't really change. So this becomes minus nr logarithm of nr plus nr. I use the Stirling approximation there. Now, when I look at this variation, there is the variation of this one times constant logarithm of nr. There will, well, let me write it explicitly. Of gr minus variation of nr logarithm of nr minus nr times the variation of the logarithm will be variation of nr divided, okay. I won't look at the variation of this nr because sum over all r nr is already fixed. That's my constraint. So the sum over all the variations of nr should be 0 anyway. So I will ignore that term. That is 0 by my constraint. Well, similarly, this term will also just give me a variation of nr. In fact, let me just, these terms cancel each other, whichever way you like. And then I have plus alpha times variation of nr plus beta er times the variation of nr. This should be 0. Now, since I included all the Lagrange multipliers, I can just set the coefficient of delta nr to equal to 0 because they will all be independent, which will tell me that logarithm of gr minus logarithm of nr plus alpha plus beta er should be 0. When, let me use this symbol, nr star is the one that maximizes omega. Well, this tells me that logarithm of nr over gr should be equal to alpha plus beta er. Now, let me make a change in the signs, because beta is just some Lagrange multiplier which I have to determine using my constraints. It's just some arbitrary constant at the time being. So I can just define minus beta as my beta. So that I will get the correct signs everywhere. Yeah, the conventional signs. Well, this tells me that nr over gr is e to power alpha minus beta er. But what is nr over gr? Well, that is the number of states per microstate. You see? Let's go back. nr is the number of copies in a cell. The cell contains gr states. So nr over gr will be the number of copies in a given microstate. But this is well, what is alpha? Well, sum of nr star should be equal to n, and sum of er nr star should be equal to u times n. So these equations determine alpha and beta. So if nr star over g, well, remember I have this ensemble, there are many copies. If I would like to ask what is PR, the probability that I pick a random copy in my ensemble, the probability that it will be in the state, in the microstate R, Well, this will be proportional to, this will be equal to, in fact, NR star over GR. This is the number of copies in one microstate, R, divided by the total number. Well, I don't really need to know what N is or what GR is. What I know is that this is a probability that depends on the microstate through e to the power minus beta ER. This is the only dependence on the which microstate I choose. And since it's a probability, it has to be properly normalized. This is my probability. Again, this is what, okay, if you go back. Let's just go over what we had done. First, I'm creating my ensemble, which is just many copies of my system. Then I will ask the question, if I pick one randomly, what is the probability that it will be in a given microstate? R. That is what I'm interested in. Because once I know that, I can calculate everything else. But my ensemble is also not fixed. I mean, I don't know which microstate my copies are. I'm just saying that they are randomly distributed somehow. And then I imagine many possible ensembles corresponding to the same system. Now, how I can determine my ensemble? Well, my ensemble is determined by if I know the number of copies inside the ensemble that are in a given state R. That determines my ensemble. Now, if I know in which microstate each one of these copies are in, that determines my ensemble. But for my probability, I don't need to know that. For my probability, I don't need to know which copy in my ensemble is in which microstate. The only thing I need to know to calculate the probability I'm interested in is how many of those copies are in that microstate. So then I'm kind of changing my question. I'm not asking which copy in my ensemble is in which microstate. I'm asking this question. What are the numbers of copies within my ensemble that are in a given microstate? Okay, so I don't know that, but I can ask this question. What are the possible values of these sets, these numbers n, r? What are my possibilities when I'm creating my ensemble? Well, I mean, I have to find integer numbers. These NRs are integer numbers, so that their sum will be fixed. Well, if you have a fixed number of integers, to me, at least it helps me to imagine that I have some holes. I just put this n of them within these holes, and I can just move one from one hole to the other hole. The total number doesn't change. I don't add new beads, if you like. I don't remove them. I just move one bead from one hole to the other hole. What are these holes, these locations? Well, they are the microstates of my system. So they're all possible microstates you can imagine. You have many copies. Each copy will be in one of these microstates. So I just imagine them as points at the sites of these microstates in some abstract space. If I move one point from one microstate to the other microstate, the total number of points do not change. So that's how I prefer to imagine it. But now, in the canonical ensemble, I have a second constraint. This constraint, which tells me that as I'm moving these points corresponding to the microstates of my ensemble, as I'm moving them around, I have to make sure that the average energy doesn't change. So if I move one of these points to a higher energy state, I have to move another one to the lower energy state, or I have to move 3 of them to a slightly lower energy state, so that the average energy will not change. So the way I move them around in this hypothetical space of microstates cannot be arbitrary. They have to be somehow related. But then I don't know how to count them. But I know how to count a particular way of moving these beads. If I just move one bit from one microstate to another microstate with the same energy, well, the average energy doesn't change. As I'm moving these points in my hypothetical microstate space, if I restrict myself to only those replacements or transferring one point to the other point among states having the same energy, I will be creating new ensembles. So now I can count those. They will not give me all my possible ensembles consistent with these two constraints I have here. They won't be all of them, but they will be most of them. Most of them meaning, well, most of them not in the sense that I will be counting more than half, but there I will introduce will be some multiple of 10 to the power 23, let's say. It won't be something like 10 to the power 10 to the power 23. But if I just make an error of 10 to the power 23, I'm fine with it. That's a very large number, but in statistical physics, that's negligible, as long as it's just a multiplicative n. Because eventually I will take the logarithm of n. What I obtain by taking the logarithm of these numbers is itself will be of the order of n. But the logarithm of n is negligible compared to n. That's what I will be using. So then my question was, how can I count the number of ways I can move these points around so as to create new microstates, new ensembles? But I will be moving them around only within states that are degenerate. Now, degeneracy, just always keep in mind that we have error bars. Whatever we measure, there will always be some error. So I don't even need to impose exact degeneracy. Well, although my system is macroscopic, for macroscopic systems, there are many states that are degenerate. So I just group them. I just group almost degenerate states. In your book, it's called cells. The Patria calls it cells. Okay, let's call it cells. Now I label these cells by R. Before I use R for the microstate, now I denote cells. And then, remember what I wanted to find is the number of copies in my ensemble that are in a particular microstate. Now I'm even changing that question. I'm just saying, okay, the number of my copies in my ensemble that are in a given cell, and R will now be the number of copies in a given cell. So now I have all these numbers, which denote the number of copies in my ensemble in a given cell. And now corresponding to these numbers and R's, how many ensembles I can create? That's consistent with the two constraints I have. Then I said, okay, if I have one copy of these numbers, every way of distributing an R copies within GR microstates in a given cell will give me a new ensemble, consistent with my constraints. I don't need to worry about moving one copy from one cell to the other cell. Okay, they will also give me some new possible ensembles, but I will be ignoring them. I won't be counting them because their number will be small, much smaller. Now next question is, how many different ways can you distribute these NR copies in GR microstates? It's GR to the NR divided by NR factorial. Okay, so this omega here is the number of ensembles having copies in the Rth cell. Again, I repeat, these are huge numbers, But the nice thing about huge numbers is the most probable such distribution, its probability will be almost 1. So I will look for the most probable one. Then I need to maximize omega, or it's easier to maximize logarithm of omega. And then I just subject to these two constraints. Well, if I have two constraints, I have to introduce two Lagrange multipliers, which I call alpha and minus beta. And so I looked at the variation as I change these NRs. And at the end of the day, I obtain this one. What are alpha and beta? Well, those are two constants that will be determined by these two equations. One is alpha just determines the normalization, beta determines the average energy, essentially. What is an R star over GR? Remember, I have in the most probable distribution, an R star is the number of copies in the rth cell. Well, GR is the number of microstates in that cell. So n R star over GR is the number of copies in one microstate. But the probability I'm looking for well, how many copies are in this rth state, microstate? Well, n R star over GR of them are in that rth state. How many are the total copies I have? N of them. So the probability that if I pick one randomly, that it will be in the rth state will be given by this ratio. I don't need to worry about alpha, etc. The only thing that depends on which microstate I'm in is this ER. So the PR is proportional to e to power minus beta ER. The total probability has to be 1. That gives me the Z, the partition function, the numerator. Again, this is already normalized. What is beta? Well, this tells me what beta is. Well, if you like, I mean, alpha is just a normalization. It determines this Z.
Could you please repeat what did you say for the alpha?
Alpha is determines this Z, normalization. Well, if you like, what do I have is sum over n R star over GR over all microstates. This should be n, or sum over all sum over all R of e to power alpha minus beta ER, because this is NR over GR, this should be n. So e to power alpha is n over, it's just a normalization. Now, the next approach, okay, we will end here today, but on Monday, what I would like to do is, okay, this is the most probable distribution of these numbers. I can also calculate the average distribution of numbers, NR. And we can actually show that this is equal to NR star. The average will be the most probable. Yeah, that's basically what all of our discussions is based on. Although we are talking about probabilities, and hence the averages, the fluctuations will be negligible for macroscopic systems. So if fluctuations are negligible, the maximum value, the average value, or the value that you will actually measure, they should all be the same. Now, I won't do all of it, but I think it's a nice exercise where you will actually use lots of things that you have used in mathematical physics. So that's something I think you should see at least once, but it might get boring. I do advise you to go over that derivation in the book before coming, so at least it will be easier for you to follow. We will be using binomial expansions, Taylor expansions, complex integrations, saddle point approximations, etc. But I enjoy it, so I will talk about it. I hope you will also enjoy it. Any questions? So hopefully see you on Monday.